Hello and welcome to the lecture number 17 of Physics 401A. In this lecture, we will discuss the forced oscillation in one dimension. Till now, we have only discussed about the case of free oscillation. Now, what is the meaning of free oscillation? The free oscillation is such a motion, such an oscillatory motion, where some system is very weakly perturbed with respect to its position of stable equilibrium, and then the source or the agent of perturbation is withdrawn immediately. Okay. Then the oscillation basically takes place under the original potential U only. Okay. Now let us assume a system where after the perturbation, the source of that perturbation continues to work there in order to feed an additional energy, okay, an additional amount of energy by another potential UE, which is a function of x and t. Now this potential can be also dependent on time explicitly. Okay, here we are just talking with respect to the the incremental dimension, that is q minus q0, and that will be x. Okay, now, and we are also assuming that this perturbation causing force is basically can be also derived from a potential UE. Okay, now since UE should maintain only very small perturbation, both UE and X should have the same order of smallness. Okay, that is something you have to understand. Then UE at X and T can be again developed by Taylor series, like UE at 0 and time t plus x times del UE del x evaluated at x is equal to 0 times this x, okay, plus higher order terms. Now you can see that this is a function of t only. Okay, and then this can be also written as the total time derivative of another function. Then this term from the Lagrangian, okay, it can be dropped because finally it will give the Lagrangian a symmetry transformation, thereby not altering the equations of motion. Okay, that's why the resulting contribution for the potential comes directly from this. Now you see that this UE has 1 degree of smallness and X itself has 1 degree of smallness. Okay, you can just take them to have the combined effect has a degree of smallness is equal to 2. Okay, and that's exactly the order of smallness which is already permitted at maximum in the Lagrangian. We are not considering higher order terms because then the order of smallness will be higher. Okay, then the corresponding Lagrangian can be written as L is equal to half mx dot square minus half kx square plus x times this del u del x, we call that f. Okay, now although it is true that at this point I am just trying to tell one thing, that although we are saying that some system is forced from an external agency, so it can happen that maybe it is also possible that this is not only the source of perturbation. Okay, this is one of the source of perturbation which can be expressed, okay, in terms of a force. Okay, the perturbation can actually be some can be given also using some impulse. Okay, but okay, here we are just talking about a sustaining force as well. So this is also for a forced system, the perturbation is also caused by a sustaining force type of thing. Now using Euler-Lagrange equation, finally we obtain the equation of motion, which is equal to mx double dot plus kx is equal to f of t. So now our equation is a non-homogeneous second order linear differential equation in x. Non-homogeneous because this term is non-zero, right? So x double dot plus omega square x is equal to 0 is the homogeneous part, and then the total, I mean the general solution, okay, the general solution of this equation will now be something like the general solution of the homogeneous part plus the particular integral of the equation having this non-homogeneous part. Okay, that's only because the equation is an equation with, I mean, an inhomogeneous ODE, that's true, but which is linear and with constant coefficients. Okay, so I'm just underlining all the important features of the equation. Then in order to find the particular integral, of course the general solution of the homogeneous part we all know, it's like the solution of trigonometric type of solution of the free oscillation. Now for the particular integral we have to know exactly the functional form of ft, otherwise we cannot do. So a very practical example is the case where the periodic, I mean the external force is periodic in nature. F of t is equal to some small f cos gamma t plus beta. Okay, and gamma is the frequency of that force. Okay. Now for particular integral, we search for solutions having the same periodic factor, that is x1 of t, that is the particular solution. We are searching in this form. Whether it exists or not, that's the question. We search by trial method. So we search in the form of x1t will be equal to b cos gamma t plus beta. So the motivation is that the variation or the periodic variation of the force will be exactly imitated by the particular solution. Okay, and that's a very reasonable assumption because the particular assumption integral basically occurs due to this non-homogeneous part, which is a cosine function. Okay, then substituting this trial solution in the original equation 7, finally we get an equation like minus gamma square plus omega square times b is equal to f by m. So this is an algebraic equation. Okay, of course you can understand that from both sides cos gamma t plus beta will be cancelled. Okay, assuming them to be non-zero. Then b is equal to f by m omega square minus gamma square, and the total general solution will now be the summation of this free oscillation solution plus this solution. So you can see that the total general solution is a superposition of two oscillations. One oscillation is with the natural frequency or the free oscillation frequency omega, and the other one is with the force or the incumbent force frequency gamma. That means the periodic force which is now acting on the system. In case omega is equal to gamma, you can easily see this one blows up. So it cannot be a reasonable solution of 7, because in that case you can see that x double dot will blow up, omega square x will be blowing up, but ft by m will be finite, will remain finite. So this cannot be a solution of this equation, right? Then what is the way out? Well, we know that this is because whenever, so in the particular solution we have this type of problem, because here in this characteristic equation gamma has a solution plus minus omega in general, right? So that's why if gamma is exactly equal to one of the solutions, for them this type of trial solution doesn't work. So for that case we have to search the suitable particular integral of the form of a complex variable, and that's much more easier. And for that, what we will do, that we define f of t, which was originally f cos gamma t plus beta, will now be written as real of f0 e to the power I gamma t, where f0 is a complex amplitude and is defined by f times e to the power I beta. Okay. Now we use the complex form of 7, that is d2yr dt2 plus omega square yr is equal to f0 by m e to the power I gamma t. Okay, so here we just use that function. So if you just try to understand what yr is, you can see here, basically, just a minute. So okay, so here okay, so yr is the yr is okay, I thought I have already written. So yr is the part for the particular integral, just okay. So where x is equal to nothing but the real of yr is just I mean written so that just to say that this is the I mean the particular integral part and not the total general solution. Okay, so it is the part which had I mean originally this form, this second term. Okay, now in this case we will have the complex equation to solve. d2yr dt2 plus omega square yr is equal to f0 e I gamma t by m. Okay, now as you can easily see, yr of the form of e to the power I gamma t, that means yr proportional to e to the power I gamma t, is not a correct guess. That you can easily check from here, right? Because this term will be then 0 and this term will be non-zero, so it's not possible, right? So for gamma is equal to omega case, we have to make a trial solution of the form of yr, which is of the form of a function of t times e to the power I gamma t. And in the simplest case, the case is just function of t to be approximated or to be substituted by t itself. So yr will be proportional to t times e to the power I gamma t, and then yr will be bt e to the power I gamma t. You do all these algebraic manipulations. Okay, I am not going into the detail, and you will have dyr dt is equal to b times 1 plus I gamma t e to the power I gamma t. Okay, and d2yr dt2 will be then 2ib gamma e to the power I gamma t minus gamma square bt e to the power I gamma t. Then just replacing all those expressions in the original equation, this equation 12, you can simply say that you have this expression 2ib omega I omega t is equal to f0 by m e to the power I omega t, and from that you can easily say b is equal to okay f0 by 2I omega m. Okay, now just a minute. Yeah, so the whole thing is like this, and this will give you this. Okay, so finally yr is nothing but f0 times t by 2I omega m, so that was just the part of b, times e to the power I omega t. Okay, and we have to take for our normal original solution x the real part of yr, and now look here the sine part comes because here e to the power I omega t plus beta is nothing but cos omega t plus beta plus I sine omega t plus beta, and here you have an I in the denominator, so it is basically the imaginary part coefficient which finally gives a coefficient of this quantity, which finally gives the solution for x, because this I will be cancelled with the I sine omega t plus beta, right? And finally x will be equal to ft by 2 omega m sine omega t plus beta. So you can see now the complete solution is looking like this, and that's why that's what I wanted to design, denote by yr. So this is the particular solution part. Now this one is no longer blowing up. Okay, but the amplitude, this part is the amplitude part, is linearly increasing with time t. Okay, so if you now draw that, that amplitude will be going to this. Okay, and it will only continue until yr is not so much, because x is actually assumed to be very very small displacements. If you remember, that's why we Taylor expanded until the first term, first non-zero term, which was the quadratic in x square type of thing. And here so x proportional to t, that's true, but that cannot take any arbitrary large value. So here you can see these are values are large, but until and unless this mod of x is remaining small, so that it's of the order of of the first order. Beyond that, this theory does not hold at all. Okay, and how to treat that general case? We have the general theory of perturbation to deal this type of method step by step. We will discuss in some of the lectures later. Okay. Now we remember. So this is the case of the undamped forced resonance case. Okay. Of course, you can understand that this term basically will always have a small contribution with respect to this. Okay, because it is something which increases with time. So it is possible that after sufficient large time, okay, when still x can be considered as small, this term's contribution will be negligible with respect to this term. This is possible. Okay. Now we talk about a phenomena of which is known as beats. Let us consider the situation where the frequency of the external force is not exactly equal but very close to the free oscillation frequency omega. Then one can write gamma is equal to omega plus epsilon, so where the epsilon is a smallness parameter or a small quantity. So epsilon is not equal to 0 but tending towards 0. Okay. And then the complex solution for the oscillation will be yt is equal to y free, the free oscillation solution, plus y particular integral, that is yr basically, what we were denoting. Here I have just written y. Okay. So that is equal to a e to the power I omega t plus b e to the power I omega plus epsilon t. That's exactly what one should write. Okay. So because I am just again searching, because omega is not exactly equal to gamma, I can always search the solution in the form of e to the power I gamma t, the particular integral. Okay, I am not in the resonant case, that's why. So the final solution will be yt is equal to a plus b e to the power I epsilon t times e I omega t. And this one is very slowly varying. That's very easy to understand because epsilon is a very small thing, so very small with respect to gamma and omega. So the frequency e to the power I omega t is an oscillation with a frequency epsilon, and this is frequency is very low, very small. So it is a very slowly varying thing. Okay. So the motion can now be considered as an oscillation with natural frequency. That means you can see that this is the, if we consider this one as the amplitude now, okay, and this one is the phase part, okay, then we can still say that this gives us an oscillation with the natural frequency still, but with a variable amplitude, and that's exactly what happens in practice. Okay. And how to get the amplitude from this? Whenever you have a complex number as here, so the amplitude will simply be the modulus of that, right? Okay. And let's say we write a is equal to, so both a and b are themselves complex as well. So I can easily write a is equal to some small a e to the power I alpha and b is equal to small b times e to the power I beta, where small a and small b are real themselves. Then at, the total a, this one, okay, so a total modulus, that is the amplitude, okay, will now be the modulus of this a e to the power I alpha plus b e to the power I epsilon t plus beta, and this will be nothing but root over a square plus b square plus 2ab cos epsilon t plus beta minus alpha. So if you just remember that the cos part will always vary between -1 to +1, then this amplitude will vary between mod of a minus b to mod of a plus b. Okay, so the basic frequency of the oscillation doesn't change, but the amplitudes are changing with time. Okay, and this is the famous phenomenon of bits. Okay, in the next lecture we will talk about the damped oscillation. Okay, thank you very much.